So this is where we left in class today. There are 5 different patterns that are often seen in writing resonance structures, and we discussed that. So once you have a bunch of resonance structures in your hand, how do you find out which one is more contributing than the other when it comes to the actual structure of the molecule? So for example, here we have an ether carbocation. This is the starting structure, and now you have a new form that you can write from this. And we know that this comes from pattern 3, where you have an electron source right next to an empty p orbital. When you have this kind of situation, then you just pull your electron from the source towards the other carbon atom, which has an empty p orbital, and you'll be able to write this new form. Between these two, which is more contributing? It is going to be this, because the carbon here has a complete octet, even though the oxygen has a positive charge, whereas here the carbon does not have an octet. So this is the most important rule. The electronegativity positive charge rule comes later. The first thing you have to make sure is the the period 2 atoms all have a complete octet. So this is more contributing for that reason. Now take this example. Assuming you have an octet, how do you now decide between 2 different structures? So let's start with this, where you have nitrogen on 2 nitrogens on the carbon. One of them is sp3, the other one is sp2 hybridized. You pull these electrons in, the carbon has to let go of these electrons so that the electrons gets on the nitrogen. Since the nitrogen here has lost the electrons, it is going to gain a positive charge, and the nitrogen here, having gained an electron, is going to have a negative charge. So this is the charge distribution on the second structure, and this comes from the original structure. And from this structure, you will be able to write a new resonance form where you only pull an electron away from the carbon, but you do not receive electrons on the other end. What I'm talking about is you just have this electronic movement going. You do not have this. So you'll be able to now go from structure 1 to structure 3, and that means your carbon gets a positive charge, your nitrogen gets a negative charge. So when you have these 3 structures, which one is going to be more contributing than the other? So look at this one. It has no charges, and it has all the second period atoms with an octet. Therefore, this is going to be the most stable. In this specific situation, you have octet on all the atoms, that is good, but you have charge separation. The nitrogen here has positive, this one is negative, therefore this is going to be less stable energetically than this one, and therefore this is going to be less contributing. And if you look at this specific form, this has charge separation, and also worse than charge separation, this has a carbon with no octet. Therefore this is going to be the least contributing form. So the second most contributing, and the least contributing. Okay, so now let us look at another example. So in this case, we have an oxygen with a negative charge based on the number of lone pairs, and here your carbon gets a negative charge, and you pull your oxygen's electrons towards this carbon, and the central carbon lets electrons go towards the terminal carbon. Okay, so between these two, this is going to be more stable. So this is going to be the major contributor between these two, and this is going to be the minor contributor. The reason this is major contributor is because here the more electronegative atom has a negative charge, because oxygen can hold on to electrons more easily. So that is that. Now you can write a third resonance form like the one you wrote in the previous one, where you start here and get here by just breaking this bond towards the carbon without pulling these electrons from the oxygen. So this oxygen has a negative charge, same as the first one. This carbon has a negative charge, and this carbon is going to have a positive charge. And this is going to be a highly unsustainable form, because it has 3 charge separations and it has 1 atom without an octet. So this is going to be so unstable that this can be essentially ignored, and therefore you'll write only 2 resonance forms for this molecule. Now let's compare this with what we have in the previous case. So here, if you look at it, this is very similar to what you have here. Okay, you have a carbon positive charge, carbon negative charge, but what you do not have is this nitrogen having a negative charge, or this oxygen here has a negative charge, the nitrogen here does not have a negative charge. So you have only 2 charges. Here you have 3 charges. Therefore, this is still acceptable, whereas this is going to be highly unstable, that you don't even bother writing the structure. Okay, so that is rule 2 discussed on 2 different contexts. Now if you go to rule 3 of finding out the resonance contributions, then you have the decision between the same charge being on different atoms. Again, we have discussed this in various places. This form leads to the other form. Here the oxygen does not have the negative charge, but it has a double bond. The carbon has a negative charge. So between these two, this is minor contributor because carbon is less electronegative. Major contributor because oxygen is more electronegative. And if you look at this starting structure, oxygen has a positive charge, and nitrogen lets the electrons in. Oxygen takes these electrons, loses its positive charge. Therefore, the nitrogen gains a positive charge. Now, between these two, the less electronegative atom, being nitrogen, has a positive charge. Therefore, this is going to be the major contributor. That's it. So now let's practice this problem. So you are given one form and you are asked to write more forms, and then after writing all the resonance forms, you are to decide which one is more stable or more contributing, which is the same thing. Okay, so the first form you can write, you will make sure that you realize this nitrogen has 2 lone pairs, lone pair 1, lone pair 2, because it has a negative charge. And you don't have to always draw the second one, but you have to have at least one that you are using to show where it is moving. And when this carbon receives these electrons, you have to break this bond. So in this case, you have to draw both arrows. You cannot just have one arrow. All right. I'm sorry, this is really slow because the usual software I use for recording is out of license duration, so therefore I cannot do that right now. Okay. So you will have a double bond with the nitrogen. And nitrogen will not have a positive charge because it had a negative charge. It's only losing the charge. Okay, negative. Then you have a double bond, and then, excuse me, that moves in, this comes in here. Again, I apologize for the terrible structures. So you have a negative charge here, and since I have a projected line, I'll say that that's just a hydrogen, and you have your nitrogen. Okay, that, and then the third form you can write is, I'm not going to show arrows, I guess you guys get the point. And then you have your double bond, negative charge here, and you have your nitrogen here. So you will be able to write these 3 forms, and you started with the original one, so you have 4 different forms. So among these 4 forms, the most contributing one is going to be this. It's going to be that. And that's because the more electronegative atom holds the electrons. and these three are going to be all equally contributing because they all have the exact same characteristics. There is going to be a slight difference because this electron is closer to a nitrogen, therefore the nitrogen pulls electrons through this bond, making this a little bit more stable, but that's very marginal. Therefore, for all practical purposes, we will call these three exactly equal. And of course, this is exactly equal as this, therefore there is no difference between these two. This one might be slightly different, but for now we will call all of them to be equal. Okay, so in this case, this nitrogen has a lone pair, only one, and you can write a new form. Because the carbon here has an empty p orbital, and the nitrogen now is going to incur a positive charge. That's a positive charge, and that's one form. And so, well, technically again you might be able to write a structure that looks like this, where you pull these arrows here, and this carbon now has to let go of this arrow, therefore the electrons go there. I mean, I don't even need to write this, but I just want to tell you in case you're confused when to decide which structures to ignore. So if you take these two electrons away from this nitrogen, which already has a positive charge, you're now going to have two positive charges because you have 1, 2, 3 electrons only, and nitrogen comes with 5. So you have two positive charges. You will get a new double bond here. This one will have a lone pair and therefore a negative charge. But as you could see, this is three charges total, and nitrogen having two positive charge is just going to be unsustainable. So you can again ignore something like this and do not even have to worry about this. So now between these two structures, this is going to be the major contributor because the other one does not have an octet on this carbon. Therefore this is the major contributor. Alright, so that is your exercise for finding out how to decide between the various contributors and see which one is more significant than the other. And now that when you have a contributing structures or set of contributing structures, how does the overall structure of the molecule look? So if you look at this form of the allylic carbocation, the positive charge is on this carbon, and the other structure you write will have positive charge on this carbon. So if you squish these two in together, you will now see that the terminal carbons are the one that have the positive charge, and the middle one will never get a positive charge because it has electrons around it at all time. Therefore, you just need to kind of get an average, or essentially what I would say is, without twisting and turning the molecule, run this into that one, and in this structure the carbon here has 0 charge, whereas the same carbon in this structure has 1 positive charge. So we can call it qualitatively a half a charge on the resonance hybrid, and the same is true for the other carbon, half a charge, qualitatively speaking again. Okay, and that is how you draw the resonance hybrid. And when it comes to delocalized lone pairs, what is the hybridization label you're going to give to your atoms? So in this case, if you look at a molecule like this, where the nitrogen is next to a carbonyl, like a C double bond O, so this is an allylic situation, as you guys know, then these lone pairs are going to be conjugated. We know that. Now the question is, what kind of hybridization should we assign to this carbon? Because it is clear that it is an sp2 in this situation, but this one looks like an sp3 in this form, and once you write a new form, you have a double bond on this nitrogen, and that looks like an sp2 hybridization. So if it's an sp3 here and an sp2 here, what are we going to call the hybridization in a resonance hybrid? Well, once you have a delocalization, the electron is not going to just sit on the nitrogen atom, it is going to always conjugate. Therefore, we will give this nitrogen, irrespective of which form you're looking at, an sp2 hybridization. So as it says here, in one structure the nitrogen is sp3 and the other it's sp2, right? So which is it? If a lone pair participates in resonance, then it occupies the p orbital all the time. Therefore, we will call the nitrogen to be an sp2 hybridized nitrogen. So don't be just confused by this one structure. If it's conjugated, it is sp2 hybridized. And same is true with this oxygen atom. If it's conjugated, then it is sp2 hybridized. All right. That is something that you want to keep in mind. So let us look at this specific situation, which is something that you need to always take into consideration, where you have a lone pair on the vinylic atom. So as you could see, this nitrogen is not only an allylic nitrogen. If you look at this bond, because carbon-carbon double bond, the nitrogen here is a allylic nitrogen. But if you look at the nitrogen with respect to this carbon, it is a vinylic nitrogen because it has a nitrogen-carbon double bond and the lone pair is on this nitrogen. So when you have this situation, even though just looking at the two-dimensional structure of this molecule, you might be tempted to write a resonance form, pulling these electrons in and pulling these pi electrons out, and drawing a new form that looks like this. This new form is not going to be possible for two reasons. The most important reasons is what is called as the consequence of an orthogonality rule. So we have to kind of get a sense for how this molecule looks in three-dimensional space, which is why I always emphasize the fact that you have to construct a molecule using molecular models. Okay, so we know that in this neutral form, this nitrogen is sp2 hybridized. So that is a sp2 hybridized nitrogen, which has three groups. Group 1 being this carbon, group 2 being this carbon, and group 3 being this lone pair. So let me get my pen. Being the lone pair. So this is group 3. All right. And as we also know, in sp2 hybridized atoms, the three groups are going to be in the same plane. It's a planar triangular. So the nitrogen is here, and the carbon and the lone pair, they are all on the same plane. And if you look at the pi bond that it is going to conjugate with, if you want it to conjugate, right? This pi bond is made up of p orbitals that is perpendicular to this plane. So this p orbital is perpendicular to the lone pair that you see on this sp2 hybridized nitrogen. And based on the orthogonality rule, which you might have heard in Gen Chem, in case you did not hear, when there are two orbitals that are perpendicular to each other, you will not be able to interchange or push those into the other. So that means this lone pair cannot go into the p orbital here. That just cannot happen. That means you cannot use this lone pair for conjugation, because conjugation means taking those electrons and putting them into the other atom. Okay. Now let me come back to this again, but let me show what is going on in the previous case. Like if you look at this nitrogen here, this nitrogen with the lone pair is conjugating with the p orbitals on this carbon, but this nitrogen is not sp2 hybridized, it is sp3 hybridized. So in an image like this, if this nitrogen is sp3 hybridized and you want to conjugate that with this p orbital, that is going to be possible because the lone pairs are going to be out of plane and more in line with this pure p orbital. Therefore, those electrons can go in to this conjugated pi bond, whereas this electrons cannot go into this p orbital. I know I previously showed the orthogonality with this p orbital, but yeah, when you try to conjugate the lone pair, as you could see here, the lone pair is going into this carbon atom. So you should be looking at this p orbital, which is the same as this one. But either way, when they're perpendicular to each other, they just cannot mix. Therefore, you won't be able to write a resonance form with the vinylic nitrogen lone pair, even though it is allylic to this carbon atom. So that is one reason. And the other reason is, when you look at the structure, this nitrogen is sp hybridized, which is very similar to what carbon has in carbon dioxide. So when you have carbon dioxide, the carbon here has two pi bonds, and that is sp hybridized. And as you know, sp hybridization is linear shape, and this nitrogen is will be forced to adapt a bent shape, which is about what I would say maybe like a 30-40 degree change in bond angle, which is not going to be favorable. Therefore, that is also another reason that this structure cannot really exist in real life. Therefore, this is not going to be something that you want to write when you're asked to write the resonance form for this molecule. So what resonance forms can you write? You can simply write these electrons moving in from here and these electrons moving out from here, and then this going back here. Okay, you will be able to write that. And for this molecule, if you write a structure like this, that is also acceptable. There is nothing wrong with this. So you are simply breaking a bond on one, putting a positive charge on one, a negative charge on the other. The rest of the molecule remains the same, and this can lead to another structure which would look like this. Okay, that's so if you pull if you pull these electrons in from here, then you will be able to write a double bond here, a negative charge, a positive charge, and a double bond here. So this is acceptable again, right? And if you pull these in and pull these out here, you'll be able to write a third form, which is now going to have a double bond and a double bond here, negative, positive. So these structures are acceptable, whereas this one is not. And how do you find out? If you have vinylic lone pair, which is either a carbon, nitrogen, even if it's an oxygen, right? If it's a vinylic lone pair, just don't conjugate that on the other side. Okay, so that is not going to be possible. So that it leads to this sp hybridized new form. Don't write that. That's it.